Hi, welcome to this session, the next session of CPP on mechanized separation logic. Our first speaker is William, talking about compositional verification of concurrent C programs with search structures, templates. Please.
All right, thank you. So the work I'm going to present today grew out of a collaboration between UIC and Princeton on verifying the data structures that are used to implement single-node databases. And in the process, we came across this work by Krishna et al. On concurrent search structure templates. So search structure templates are this really neat idea of decomposing the verification of a data structure, in particular a search data structure, like the kinds of B trees and binary search trees we were interested in, into reasoning about concurrency and reasoning about the data structure. So the theory is you should be able to take a sequential implementation of a binary search tree or a B tree or something like that, and verify it sequentially, and you should be able to take a description of a concurrency pattern, like lock coupling or optimistic concurrency, and verify that without thinking about the data structure. And then you put these two together and automatically get a verified concurrent data structure. And then if later you decide you want a different concurrency pattern or a different data structure, you just have to verify that one piece, either a sequential verification of the data structure or a concurrent but data structure agnostic verification of the concurrency pattern, and you immediately get your new verified concurrent data structure. So in theory, if you use this approach to verify n templates and m data structures, you'd get n times m verified data structures, more or less for free. The original implementation of the approach was on top of flow interfaces, which is a framework for reasoning about graph-structured data structures in separation logic. But the graph structure isn't really fundamental to the approach. And the original implementation was also sort of split between two provers, with the concurrency patterns verified in Iris, a Coq-based separation logic theorem prover, and the data structures verified in Grasshopper, which is a more automatic separation logic prover. But again, there was nothing really fundamental to either of these to the search structure template approach. So what we wanted to do was to see if we could reconstruct the same approach in the Verified Software Toolchain, VST. VST is a separation logic-based theorem prover for verifying specifically C programs implemented in the Coq theorem prover. And its big selling point is that it's attached to the C semantics of CompCert, the verified compiler. So if we prove something about a C program in VST, then what we've proved actually gives us some guarantees about compiled and executing assembly. So then what we were interested in doing is re-implementing the template approach in VST, using sort of as little extra theoretical stuff as possible, and seeing if we could get this sort of compositional and reusable proof for real C implementations, or at least realistic C implementations of concurrent data structures. So in this talk, I'm going to walk you through exactly how the concurrent search structure template approach works, how we implemented it, and the ways in which it did and didn't work the way that we wanted it to. So first of all, if we want to verify a data structure, a search structure with the template approach, fundamentally what that means is we have these three core search structure functions, insert, lookup, and delete, and we want to prove some reasonable specification for each of them. But if you want to use the search structure approach, you can't just write these functions. You need to implement them in a very particular way. Specifically, you need to start by implementing a function called traverse. And this traverse function is the core of the concurrency template. It describes the concurrency pattern that you're going to use in the data structure, and all three of these top-level functions, insert, lookup, and delete, need to be implemented by calling traverse. And all traverse does is walks through whatever data structure you're looking at, using whatever kind of concurrency pattern you're trying to define to figure out which node is the one where a given key belongs. So in insert, that might be where we want to insert the new key. In lookup, that might be where the key is already in the data structure. But all of these functions are just going to be implemented basically by a call to traverse and then whatever operation they actually want to do. And there's two key features of this traverse function. First, it needs to actually implement whatever concurrency pattern it is that you're interested in implementing and verifying. So this is a lock coupling template, otherwise known as hand-over-hand locking. where we always hold we acquire the lock on the next node that we want to go to before we release the lock on the current node. So you can see that right here in our sum case. And so that's the template that we're trying to verify, the concurrency pattern that we're trying to verify in this case. And the other thing about this template is that it's supposed to be totally agnostic of the data structure that we're looking at, which means that the template itself can't know how to figure out which node to go to next. Instead, it calls this function findNext, which from the perspective of the template is a black box that can be implemented differently by different data structures. So then if we want to attach this template to a data structure, we have to implement a findNext function for some particular data structure. So for instance, in a binary search tree, maybe findNext just compares the key we're looking for to the key in the current node and tells us whether to go to the left or the right child. And the data structure also needs to implement what we call these op functions that actually execute the specific operations, insert, lookup, delete. And those should be implemented in exactly the same way we might implement them in a sequential data structure, right? So on the left, we have the implementation of a binary search tree, sort of broken up into pieces, but all totally sequential and unaware of concurrency. On the right, we have the implementation of hand-over-hand locking, totally agnostic of the data structure that we're interested in. And putting all these together, we get implementations of the top-level insert, lookup, and delete functions. Of course, these implementations are the ones that were used in the original template work and written in a simple toy functional language. We have to actually implement these in C if we want to verify C implementations, but that translation isn't too surprising. findNext and the other sequential functions are more or less exactly what we'd expect. For traverse, we changed it from a recursive function to a loop to make it more idiomatic C code, but it's still doing basically the same thing. You can see we have our hand-over-hand locking, our lock, acquire, and release, and we have our call to findNext, which implements the data structure logic. All right, so that's the code that we're trying to verify. Now, what are we trying to prove about it? In the search structure template approach, the top-level specifications we're trying to prove about the data structure operations are written as logically atomic triples. In logical atomicity, it's a variation or a kind of separation logic specification, but one in which we have two kinds of pre- and post-conditions for each function. We have what we call a private pre- and post-condition. Here, what we've written as ref, which is the resources that are actually owned by the thread that's, for instance, calling the function. And then we have what's called a public precondition, which is resources that aren't really owned by any thread, but rather are adjusted atomically to reflect the impact of the data structure operation. So in this case, for instance, we're saying for the insert function that the calling thread has to own a reference to the data structure to call it, and its effect is to atomically transition from a data structure whose abstract state is some map to a data structure whose abstract state is that map, but with the new key-value pair added. The way to think about these atomic triples is basically that they're specifying that the state of the data structure has to not be visibly changed by the data structure operation, right? So we have this abstract state M. The insert operation, for instance, can access the state M, but it can't make any visible changes to the data structure until it reaches some linearization point. And at that linearization point, it needs to atomically transition from the current state M to the new state in which the key-value pair is inserted. So basically, these triples say the effect of the insert operation appears to take effect atomically at a single point in time, transitioning from the original map to the map in which we've done the insertion. So this idea of logically atomic triples originally comes from the Tada logic. It is nice, it's the condition that we want to use, because it's been proved that if we prove triples that look like this for each of our functions, then what we get is linearizability, that you can't distinguish between the concurrent implementation of the data structure and a sequential implementation of the same data structure. And this logical atomicity has been formalized and mechanized in Iris in terms of its invariant and view shift mechanism, and that was what was used in the original template work. In work leading up to this, we kind of hacked invariance and go state into VST so that we could write and prove triples that look like this, and that's what we used for this work. I will be talking tomorrow in the separation logic section about a much better approach that VST takes to invariance and atomicity now. So definitely catch that if you're interested. But the upshot is that when we have a C program like this, basically what we need to prove, the way we need to verify it, is to say that at each point, all the way through the call to traverse here, the insert operation doesn't modify the data structure in any visible way. And then when it gets to either of those two linearization points where it actually inserts the value, then we atomically transition into a new state in which the key value pair has been added. So that's what we wanted to prove about our data structures. And then to verify our, in this case, lock coupling concurrent binary search tree, we needed to prove these specs by proving for the traverse function a somewhat more complicated atomic specification, and for find next and the other data structure components, ordinary sequential Hoare triples describing their effects on the data structure. For the traverse function, I know this is a bit complicated looking, but really the thing to note here is just that the public or shared part of the pre and post condition is the same before and after, so that traverse operation, all it's doing is going through the data structure and finding the particular node where we want to perform an operation. It isn't modifying the data structure in any visible way, and so it's safe for us to use before we've hit the linearization point of the insert. And for find next, insert, lookup, delete, we expect to give them exactly the same pre and post conditions that we would if we were verifying the data structure in a sequential setting. And the proofs, likewise, are exactly as we'd expect. At least that's the theory. And then what we should be able to do is prove correctness of each of our insert, lookup, and delete using these triples for traverse and find next, and get our verified concurrent binary search tree. So that's how the process works on paper. How did it actually go? Well, the proof of traverse is definitely where most of the proof effort ended up being. So we have to define our abstract state of the data structure, including ghost state and concrete resources that make it up. We have to define invariants for the various locks. We have to define a loop invariant for traverse. But all of this went fairly conventionally. The proof more or less followed the outline that was used in the prior template work, modulo the transition from recursive functions to loop invariants. There were lots of details of C programs and so on that we needed to attend to, but ultimately the proof of correctness for the traverse operation went as expected. Somewhat surprisingly, the place where we encountered more difficulty was with the proof of the sequential operations. So let me show you a bit of what problems we ran into.
Should we be seeing different slides?
I don't think so. The first problem didn't come up with the lock coupling template, but did come up with another concurrency template that we looked at called the give up template. So here again was our code for the lock coupling template. And here's the code for the give up template. So give up is a form of optimistic concurrency control where we don't hold the lock on both the node we're leaving and the node we're going to every time we make a transition. Instead, we only hold one lock at a time. And the cost of this is that we may find that we've gone to a node that then got swapped out from under us. So we're no longer at the right node to perform the operation we're trying to perform. So the way that the give up template deals with this is that we have an extra check called in range that we have to perform each time we get to a new node. And if that check fails, we just start the whole thing over. So you can see here we make a recursive call to traverse all the way back at the root node R. So hence give up. And that in range function is something that we need to implement as part of this template to finish specifying this function. And it's just we annotate each node in the data structure with a minimum and maximum key value that can appear in this case, its subtree. And we check that the key we're looking for is in that range. So all of this is pretty straightforward, and we can verify the give up template along these lines. But the fact that we added extra fields to the node data structure makes this separation a little less clean than we might want it to be. So for instance, in our sequential insertion operation, if we're going to add a new node to the tree, then we need to initialize its minimum and maximum fields as well. But those min and max fields aren't part of the binary search tree. Binary search trees don't need to store min and max. They're part of the template, the thing that's supposed to be our totally data structure agnostic concurrency part of the program. So we can sort of repair this by insisting that every time the data structure logic creates a new node, it sort of calls back into the concurrency template to initialize whatever data the concurrency template might need, which in the hand-over-hand locking case was nothing. In the give-up template was these extra fields. But it definitely at least complicates the picture of the relationship between the data structure and the concurrency components of the verification. Right, before we had top-level operations use templates. Templates call into the data structure, but the data structure didn't call template functions. Here now, it seems like, at least if we're going to add new nodes for this kind of data structure and this kind of template, we need some more complex relationship between the template and the data structure. And it still works. We still have a verified insert op, but it doesn't separate as cleanly as our original idea suggested. Another thing that turned out to be a little bit more complicated than we expected was deletion. So I said before when I was talking about using traverse to implement these top-level operations, that each of these operations is basically just a call to traverse to find where we want to do our data structure operation, and then a call to a sequential data structure operation that makes a local change to the tree. But that's not usually how deletion works in binary search trees. For instance, if we want to delete the node 6 in the tree we have here, usually the way we do it is first by doing some rotation. We move the node 6 down through the tree and move other nodes up so that 6 doesn't have both left and right children. And then when we remove 6 from the tree, we can just move, if it has one child, we can move that child up in the tree. If it has no children, we can just take it out entirely. So this is a very standard deletion process, but it's neither a data structure specific concurrency agnostic operation nor a data structure agnostic concurrency specific operation. Right? It needs to know that we're a binary search tree. This operation doesn't even make sense unless we're a binary search tree. But it also needs to be able to move through the tree, access multiple nodes, acquire locks if the nodes happen to have locks, and so on. So there's no clean way to separate this kind of deletion operation into a data structure operation and a concurrency operation. And in fact, this isn't news. This was already mentioned in the original template paper, where they essentially sort of quietly identified a third kind of operation that they called maintenance operations. And maintenance operations aren't concurrency agnostic. They aren't data structure agnostic, but they are no-ops. So for instance, this rotation operation, it moves nodes around, but it doesn't change the set of nodes in the tree. So we need to know both what data structure and what concurrency pattern we're using in order to verify this kind of deletion function, but its specification is relatively simple, so maybe it's not as hard to prove as the general combination of data structure and concurrency pattern. So this means that we can't just freely combine N data structure and M templates and get N times M verified data structures for free, but templates still reduce the amount of work that we need to do if we want to verify multiple concurrent data structures with, or multiple concurrency patterns. So here's a quick summary of the proof effort that went into our verifications. We ended up proving correctness of these two templates, lock coupling and give up, and one data structure, the binary search tree. Most of the effort went into proving the correctness of the traverse functions and coming up with their loop invariants. And the total size of the proofs was about the same as the size of the proof that we did for a non-templated verified binary search tree with hand-over-hand locking, which doesn't sound good, but actually we think is a pretty big win, because since most of that effort was in the concurrency template, if we wanted to then verify another data structure, we should be able to reuse a very large amount of that proof effort. Compared to the prior work with templates, it's kind of hard to compare directly, since half of their proofs were done in an automated theorem prover, but we definitely had more lines of code in total by far, which we should expect since we're doing reasoning about real C code. We have to worry about things like integer overflows and the structure of structured data. We had to convert recursive invariance into loop invariance, and so on. So to sum up, we re-implemented the concurrent search structure template approach independently of the flow interface framework in the Verified Software Toolchain so that we could apply it to C data structures and get end-to-end correctness guarantees for concurrent data structures implemented in C. And we found that templates mostly lived up to what we were hoping to get out of them, and that they let our proofs largely decompose between concurrent and data structure-specific aspects, and we get some amount of reuse of the proofs that we've written. But also we found that the boundaries weren't quite as clear as we'd hoped, and there are, at least for binary search trees, proofs that we do have to do once per data structure times concurrency combination, rather than once for a template or for a data structure. What we'd really like to see is a way to formalize the decomposition that we've talked about and actually make it a framework in which that decomposition is explicit. So for instance, in Calc, we might define these things as type classes and say we have a data structure type class. It provides these functions, find next in the operations. They meet these specifications. Then we have a template type class that takes a data structure as a parameter and defines a traverse function, and maybe also has some obligations, like you can only use this template if the data structure has certain fields or has certain properties. And then that we could prove our insert proof entirely at the level of these type classes and actually just immediately get a verified data structure with a given underlying data structure and concurrency pattern by plugging in the instances of whichever type classes we want to use. So we've started some work in that direction, but there's definitely more to be done to actually formalize this decomposition and get it working in a mechanized theorem prover. And ultimately, we want to come back to our original goal of proving correctness of database data structures, things like mass tree and wormhole, that are concurrent search structures, but often mix a bunch of different concurrency patterns, including lock-based ones, optimistic ones that use atomic operations, and so on. And we think this will be a really good fit for the template approach. But first, we need to get the template approach to actually work the way that we want it to in the theorem prover. So that's all that I wanted to say for now. I'm happy to take any questions.
We have plenty of time for questions.
I'm Adam Japala from MIT. I was wondering, and you're kind of getting at this with this slide, how representative of the state of the art, the state of practice, algorithms with trees of locks actually are. It sounds like in general, there'd be pretty bad cache performance from any algorithm that worked like this.
Yes, so actually mass tree does use locks for some of its levels and some of its operations.
Okay.
And I think that's not 100% state of the art, but it's definitely on the list of things people bring up.
Okay, thanks.
Other questions?
Andrew Appel from Princeton. One kind of tree maintenance operation you didn't mention is in balanced binary search trees and other balanced tree data structures, rotations. Mm-hmm. So are rotations going to be messy? And this is really, I guess, a reflection on the original notion of templateizing, not on any proof technique in particular, right? Yeah, I mean, I think rotations are basically as described. The original paper also talks about splitting nodes in B+ trees. It's all, I mean, messy, maybe, only as messy as verifying concurrent data structure operations was all along. It's mostly just that they don't get significant benefits from the decomposition of the templates.
Gregory Malika. The traverse that you have is very similar to like a partial alto sort of function. How easy would it have been to do this decomposition by passing a higher order function to do the actual altering and fuse the maintenance operations?
So you're saying like if traverse took things like insert op as arguments? Yeah, I don't think that would be any harder. I mean, you need a separation logic that supports that, but VST and Iris and all do. So yeah, I think it would be basically the same difficulty.
Anyone else? Any other questions? By the way, I don't know where the next speaker is for the next talk. Yeah, okay. Yes, so maybe I can ask a question while the switch is happening. You said that some work that you're going to talk about tomorrow, but I was curious about what the issue is about for stating and proving those logical atomic triples.
I mean, the issue is that like 3 years ago, VST didn't have go state. And so we hacked it in, and then we found a better solution, which I will talk about tomorrow. Okay. It's basically VST is Iris now.
Thank you. Let's thank the speaker again.